Here we'll consider eigenvalues and eigenvectors of stochastic matrices. See the definition. A probability vector is a vector with non-negative entries that add up to 1. For a square matrix, if each column of the matrix is a probability vector, then we call it a left stochastic matrix. A right stochastic matrix is defined such that each row is a probability vector. If we say simply a stochastic matrix, then we mean a left stochastic matrix. A stochastic matrix is also called a probability matrix, transition matrix, substitution matrix, or Markov matrix. Okay, see the lemma. If P is a probability vector and T is a stochastic matrix, then their product, TP, is a probability vector. It can be proved easily. V1 to Vn are the columns of T, then the product can be written as a linear combination of the columns of T. That is in Rn. So we try to get the sum. Sum of Q is the same as sum of this linear combination. Now we consider sum of each the column of T, then that must be 1. So we have this summation. Now these are entries of P, which is a probability vector, so that it must be 1. Okay, so we finished the proof. A finite Markov chain is a sequence of probability vectors together with a stochastic matrix T such that x1 is tx0, x2 is tx1, and so on. Once we start with a probability vector, then x1 must be again a probability vector, and so are x2, x3, and every later vectors. This can be written as a recursive relation, xk plus 1 equals txk. Each xk is called a static vector. Now, let's start measuring eigenvalues of stochastic matrices. In order to do that, particularly one norm is very useful. Here we begin with a definition of the P norm. For vector in Rn, the P norm is defined as in this equation. We take absolute value for each entry in the vector, and P power sum, and finally 1 over P power. When P is 1, that is simply the sum of absolute values. And if P is 2, then that is square sum and square root. T is a stochastic matrix, then for arbitrary choice x in Rn, tx1 norm is bounded by x1 norm. We can prove it when n equal 2, and the argument can be generalized. Okay, n is 2, then T can be written in this way explicitly, and X has two components. Now Tx will have two components. Here, Tx one norm is addition of absolute values. For the first component, here we have absolute value, and the absolute value of the second one. Now, from elementary mathematics, we know that the absolute sign can be applied for each one with this inequality. Now we rearrange the terms. For the absolute value of x1, we have these two, t11, t21. For absolute value of x2, we have t12, t22. So we put here. Now this addition is the column sum for the first column, so it must be 1. And this one is the column sum, so it must be 1. So we have here, now this addition is the same as the x1 norm. So we reach at this one when n is 2. But this argument can be easily applied for general n, so that we can finish the proof. As a corollary of the theorem, we have this one. T is a stochastic metric, then every eigenvalue of T is bounded by 1 in modulus. That means that if we have TV is lambda v, then absolute value of lambda is bounded by 1. Now, it can be easily proved. We start with a TV equals lambda v. Then here TV 1 norm is the same as lambda v 1 norm. And a property of norm is here, the scalar multiple can go out with the absolute sign. So this quantity is the same as that one. Now we try to use this theorem, and for arbitrary x is true. So for v, it must be true. So TV 1 norm is bounded by v1 norm. Now we focus on this inequality, then we can reach at that claim. Okay. So far, we found that every eigenvalue of a stochastic metric is bounded by 1 in modulus. Now, here we'll see the number 1 is an eigenvalue of any stochastic matrices, and we'll try to see its corresponding eigenvector. Here we have a theorem. T is a stochastic metric, then the number 1 is an eigenvalue of T. We can prove this theorem in 2 different ways. Okay, let's see the first one. First of all, we know that determinant of T transpose minus lambda I is the same as determinant of T minus lambda I. By solving this equation equals 0 for each one, we can find eigenvalues. So this equality means that the T and T transpose have exactly the same eigenvalues. Now we consider all one's vector. Here is a vector in Rn having 1 everywhere. Now we multiply T transpose and the all one's vector. Then in T transpose, okay, that is the metric, and this is all ones. Now each row in this product, each row and the vector here dot product will be performed. But this dot product is just because it's all ones, the result must be sum of this row. Now, originally, T has column sum 1. So here, T transpose has row sum 1. So that in right side, all value must be 1. So we reach this one. That means 1 is an eigenvalue of T transpose. Because T and T transpose have exactly the same eigenvalues, the number 1 must be also an eigenvalue of T. That is the first proof. How about the second proof? Here we construct T minus lambda I for lambda is 1. Then we reach this matrix. Now we apply replacement operation. So for each one, we add this one to the bottom. And second row, add to bottom. And here, m minus first row, and add to bottom. Then the bottom row will become whole addition, which is 1 minus 1. So this position will be 0. Again, similarly, that will become 0. So that eventually the bottom row will be a 0 row. Now, determinant of this matrix and determinant of the transformed matrix will be the same. But when a row is 0, then we know the determinant is 0, so that T minus I has a determinant 0, which means that now 1 is an eigenvalue of the matrix T. Okay? The eigenvector V corresponding to the eigenvalue 1 is called a steady state vector of T, and it is also called a Perron-Frobenius eigenvector or stable equilibrium distribution. The steady state vector represents a long-term behavior of a Markov chain. And long-term behavior is one of the most interesting aspects of Markov chains. Okay, now we'll try to find the steady state vector. T is an n by n regular stochastic matrix. Then T has a unique steady state vector Q. Here, regular means that some power of T after several multiplication, or original one, or after some power of T, every entry becomes positive. And then it is called a regular stochastic matrix. Once the stochastic matrix is regular, then it has unique steady state vector Q, and the entries of Q are strictly positive, and the steady state vector can be computed by the power method. So we just multiply T each time, then later on it is converting to the unique steady state vector. So it is a sort of a long-term behavior of Markov chain, and where x0 is a probability vector, and you may start with arbitrary probability vector, and when you use this power method, then it is converting to the unique steady state vector Q. Let's say this example. Find the eigenvalues and corresponding eigenvectors of the transition matrix. For each column, the sum is 1. Now, we implement a Python program by using numpy Now we make a matrix T here, exactly we implemented, and by using the linear algebra EIG function, we try to find here eigenvalues and eigenvectors. So we print out and we'll see the result. And from eigenvectors, first eigenvalue will be 1. The largest eigenvalue will be 1. And the corresponding eigenvector will be the first column of V. So we choose the first column and now scale by its sum so that the V1 will become a probability vector. So we print out. Now by using power method, start from 1, 0, 0, and we multiply T again, and print out. And we try to multiply 10 times of the matrix. Let's see the output. For the matrix, eigenvalues are here. The largest eigenvalue is 1. We know for every stochastic matrix, and if it is a regular, the example matrix is a regular stochastic matrix, and the largest eigenvalue is 1, and then these eigenvectors, and the first column, the corresponding eigenvector, must be unique state vector when it is scaled as a probability vector. So we from this one we scaled to get that one. Now from 1, 0, 0 we multiply once, twice, and 10 times. From this one it is converting to the unique state vector. That one and that one is the same. If you start from some other vector, as far as the initialization is a probability vector, then you reach at the same unique state vector. Finally, I'll mention this one. Some eigenvalues of a stochastic matrix can be negative. For example, we apply a row interchange operation to the matrix T in this equation. So here, this row and that row will be interchanged. Then again, the column sum must be 1 for every column. So here, by using Python implementation, you can do this way. For the matrix T, now that will the select first row, row 1, row 2. In Python, the index starts from 0, so that there is a second row, third row, and that is now interchanged row, so that this line will interchange the last 2 rows. Then the resulting matrix is still a stochastic matrix, and you can easily check that its eigenvalues are here 1 and this number, and the last one is negative. So some eigenvalues of stochastic matrix can be negative. Okay, that's it. Thank you.